different model for light. Well, there was this guy, kind of late 1800s, Max Planck, who was doing, quite a famous physicist, you might have heard of him. He was doing experiments with black bodies, and black bodies, an ideal black body is something that, an ideal black body actually is if you get a box and you paint the inside black and then you make a tiny little hole in the side of the box whose inside is black. That tiny little hole is a perfect black body because any light that you shine into that hole isn't going to come out. So a black body is perfectly absorbent. It absorbs any light that's incident upon it. And also what's interesting is that as we increase the temperature of a black body, it starts to radiate. And we're kind of familiar with that. Like we know that our stove, when it's kind of cold, doesn't change colour, but as it starts to heat up, first of all it glows a little bit red, then a little bit orange, then a little bit kind of yellow as it gets really, really hot. And so we're kind of familiar with the idea that as we heat things up, the colour of the light that they emit changes. And so by studying this phenomena, black bodies, Max Planck came up with this idea that light kind of, the energy from light comes in chunks, comes in lumps, and the amount of energy that's carried by each chunk of light depends on its wavelength, depends on its frequency. And so, kind of without any justification for it, he wrote down that energy is equal to HF. And that curly H, we have to do a curly H, it's not just a normal H, it's like one with a curly tail on it. So that's a really important equation. The E is the energy of, well, he didn't know it at the time, but it's a photon of light measured in joules. The F is the frequency, and the H is what we now call Planck's constant. And so Planck had kind of thrown this equation out there. This equation was floating around, and it was Einstein who got his first Nobel Prize by explaining the photoelectric effect. And the photoelectric effect, the way he explained it, he's like, I know what's happening. He said, that Planck guy, he was onto it, right? And what's happening in the photoelectric effect is that the kinetic energy of the electrons is just equal to the energy that the photon brings in, HF, minus however much it takes to release it from the middle, which is, he used the symbol phi. And so that's an equation just of energies, eh? So we can either do that equation using electron volts, or we can do that equation using joules. So Einstein explained the amount of kinetic energy released as a single electron interacts with a single photon in the metal surface. And this was quite different to how we've been thinking about this whole phenomena before. When we think about a wave, it's kind of like if you have a lump of driftwood on the beach, and as the waves roll up, they push that driftwood up the beach a little bit at a time. Whereas, and you could be moving, one wave could move multiple little bits of driftwood a little bit up the beach. We kind of think about the waves being the light and the driftwood being the electrons, and we're doing work on it, moving it up the beach. So Einstein's explanation of this is kind of like you've got some frigate sitting out off the coast firing missiles at the driftwood, which kind of move it in one fell swoop right from the bottom of the beach right up to the top of the hill on the far side. So instead of like one wave of light interacting with all of the electrons in the metal surface, we break light into like a stream of photons, like a shower of photons, and each individual photon interacts with a single electron to either release it or not release it. And so if the energy of the photon is big enough, if the energy of the photon is bigger than the work function of the metal, then the electron is released, and that leftover energy is seen as the kinetic energy of the photoelectron. What's going to happen if this HF isn't big enough to release this? What's going to happen to that energy of the photon?
Releases heat.
Releases heat. What happens to a metal surface on a sunny day, right? It heats up. So photon energy that isn't great enough to release electrons is seen as heating in the metal surface. And so this is a graph, right? Look at this. Y equals mx plus c. We can graph this thing and we can make a lot of sense out of it. And so we might get a line like that. This is what we might see if we change the frequency, change the colour of light, like from low frequency, like red light, up to high frequency blue light. We measure the energy of the electrons being emitted each time. We might get a graph that looks something like that. And we know Einstein's rule is that EK is HF minus phi. What important values can we drag off that graph? It's a y equals mx plus c graph, eh? What's the graph? It's the h, right? So Planck's constant is the gradient. The gradient is Planck's constant. What's the y-intercept? Yeah, it's the work function of the metal. And so if you want to know how much the work function of the metal is, you do this experiment and you get some points up there, you draw a line through them, and where that line crosses the y-axis, that's the work function of the metal. What about the x-intercept? What does that represent? Yeah, it's the when they go across or when they don't go across. So if we're up here, we're getting positive kinetic energies. If we've got negative kinetic energy, what does that mean about our photoelectron? It hasn't even been emitted, like we haven't got enough energy to overcome the work function. And so this value, the x-intercept, we call it the threshold frequency, which is the minimum frequency at which photoelectrons will just be released, and then unless we're pulling them across the gap, they're going to be immediately reabsorbed by the metal.